So this is the next talk. This is some structural testing of ultra high performance concrete, or UHPC shear keys, that we did here at NMSU. I'm going to start off with a little bit of background on just what shear keys are, because not all of us are structures folks, I guess. And then I'll talk about the UHPC mixture, some preliminary testing that really focused on bond strength between the grout and substrate concrete. And then I'll talk about the experimental methods for the structural testing and the results, and wrap it up with some conclusions. And the overall objective of this work was to just assess the potential for using UHPC as a grouting material for shear key repair. And if we start off with what shear keys are, they are these pockets really between adjacent girders that we grout full so that we get load and shear transfer across the interface, so that more than one girder will carry the load applied to a given girder. So we're basically distributing the load laterally across the superstructure of the bridge. And in some cases, we may actually have this lateral post-tensioning to keep everything cinched together. And in terms of durability, one of the big things is the bond between the grout and the girder. And when that bond breaks, oftentimes that is where degradation starts and then accelerates. So bond is an important part of the problem. The UHPC mixture that we used, this is really comparable to even the proprietary mixtures. The one thing that we do differently here at NMSU is we produce our UHPC with local materials, and we use a lot of fly ash. Most of the proprietary mixtures get by primarily with silica fume. We try to keep costs low from a sustainability perspective, so we try to use as much fly ash as possible for the supplementary cementitious materials. The preliminary testing, that's the bond strength testing. We ran some slant shear tests, some split cylinder tests, and some direct tension tests. In general, we were able to get bond strength that was adequate even with very little texture. So when you look at the texture depth here, that we got adequate strength for the slant shear and the split tension tests, it's very, very small, 0.02 of an inch. This is minuscule compared to the 1/4 of an inch minimum macro texture depth that ACI recommends. But we were able to hit that strength very easily. Where we ran into problems was the direct tensile strength. And for the direct tension test, we could get by with very little texture, but we couldn't get by with grinding the samples. And we like to grind samples in the lab because they're small, it's convenient, and it doesn't break the specimen, but it plugs the pore system, which is why we didn't hit strength all the time with the direct tension test. And to accommodate that, we had to go to chipping. We basically had to open up the microstructure in addition to the macrostructure. Okay, for the structural testing, what we tested were 2 girder assemblages. So down here on the lower right part of the figure, you see these side-by-side girders, and grouted the shear key with one of 4 options that we'll talk about on the next slide. And then what we did for the testing was we loaded one of the girders and looked at the behavior of the stems for all 4 stems, the 2 stems from each of the 2 channel girders. And in this presentation, all I'm going to talk about is the mid-span deflection. This was a full-scale 25-foot span with girders that were taken out of a bridge back in 2016. And the 4 cases that we looked at were cyclic loading, 1,000 cycles. The first test used what we called improperly bonded UHPC grout. So basically, we treated this as the worst case scenario. Basically, we assumed the contractor was going to make very little effort to prepare the shear key for the grout. So basically made no effort on the surface preparation of the substrate, just grouted the shear key with UHPC grout. The second test, we used a non-shrink grout from NMDOT's approved products list. And in both cases, those were loaded to a mid-span deflection of 0.4 inches. This was the maximum expected in-service deflection under design loads. So loaded it to that deflection 1,000 times. And then we came back and said, you know, we really need to isolate the behavior of the adjacent girder. So what we did was we tested just the loaded girder with no adjacent girder, basically isolating the behavior of the adjacent girder by subtracting the behavior of the loaded girder out of the combined configurations. So ran the same load rate as CL1 and CL2, but we didn't run as many cycles. There's really no need for conditioning when there's no shear key there. And then cyclic loading 4 was the properly bonded or properly grouted UHPC shear key. Basically ran the same load rate as CL1 and CL2, again loading to maximum expected in-service deflection. And then after that fourth test, we took that assemblage and loaded it to what we call ultimate loading. Basically, we ran the deflection all the way up to 2 inches in increments, so 5 times the expected maximum service load deflection, just to see what would happen. Basically, it's a tremendous overload scenario. So when we look at the behavior, the 4 lines that you're seeing here are the stems of the girders, the deflection at mid-span, and what we see is linear behavior for the entire 0.4 inches of deflection, 1,000 cycles, and everything seemed to behave quite well. Average deflection between the exterior stem of the loaded girder and the interior stem of the unloaded girder was 0.04 inches. That doesn't really mean anything yet. It's going to be compared to numbers that come up. And the difference between the interior stems of the 2 girders was 0.017 inches. So again, it's the first test, but what we saw was excellent behavior. Even with no effort to prepare the girders for the grout, we got a grouted shear key that stayed bonded through the entire full range of expected deflection, and it seemed to transfer load effectively across the 2 girders. So we removed that improperly grouted UHPC shear key, regrouted with the non-shrink grout from the NMDOT approved products list, and again, linear behavior. The deflection difference between the exterior girder of the loaded girder and the interior stem of the adjacent girder this time was 0.081 inches, almost exactly the same as the 0.084 that we got on the first test. And the average difference in deflection between the interior stems was 0.015 inches, again almost exactly the same as the 0.017 that we got for the first test. So essentially the same mechanical behavior. It may be a little bit stiffer, but within the resolution of the equipment that we were measuring with. So everything looked good, very comparable. Load 3, or cyclic test 3, was just a single girder, again trying to isolate the effects of the adjacent girder. And what we saw was that it took about half the load to induce the same deflection. And what that's really telling us is that if you use one girder and it takes half the load to get the same deflection, then the second girder in the other tests was actually carrying nearly half the load, which is exactly what you want from an effective shear key. And for cyclic loading 4, this was the test with the properly bonded UHPC shear key. And this time the deflections got a little bit bigger. The difference between the exterior stem of the loaded girder and the interior stem of the adjacent girder was 0.14 inches. So numerically, it's a little bit larger. Percentage-wise, it's actually quite a bit larger, but still, it seemed like effective load transfer across the 2 girders. And the average difference in deflection was 0.04 inches between the interior stems. Again, a larger number, big percentage increase, but a very small numeric increase compared to the first 2 tests. So what it looks like when we compare this test to the non-shrink grout test is that the non-shrink grout test looked stiffer, but we actually saw a tighter hysteresis, so less loss of stiffness than what we saw with the non-shrink grout through 1,000 cycles. So I would say it's pretty close to a wash in terms of performance. Very similar mechanical performances between the two grout materials, but I'm going to give the edge ever so slightly to the non-shrink grout. And then for ultimate loading, basically we loaded it up to 5 times the maximum expected service load deflection. And up here at the top, you actually see the curve start to lay over a little bit. We got a little bit of yield going on there. But even at the end of that 2 inches of deflection, the shear key was still performing adequately. We still got effective load transfer across the girders, across the shear key. So to wrap it up with some conclusions, basically what we saw was that the bond seemed adequate even when we didn't make much of an effort at all to prepare the shear key on the girders. And we never did use lateral post-tensioning to keep the assemblages together. We just didn't need to. The bond was adequate. That's kind of the nature of laboratory testing. We don't have the thermal effects that we would see in the field. In terms of the structural performance, I'm going to say that the non-shrink grout slightly outperformed the UHPC grout. And since the UHPC grout doesn't really have a mechanical benefit, it's essentially comparable to the performance of the non-shrink grout. So if we're going to specify UHPC grout, it really should be only on the basis of durability and economic considerations. It shouldn't be for mechanical performance reasons. So with that, I'm going to wrap this up and take any questions if anyone has any.